Hi, it's Joe Miller again, and this is part 2 of my 3-part series on low-power design essentials for wearables, IoT, and mobile devices. Okay, let's get started with our discussion about microcontroller selection and utilization. Now, microcontroller selection may not always be based on the best or the most efficient microcontroller for the job. Your decision to choose a particular microcontroller may be based on your existing investment of in-house legacy tools and libraries. It may also be based on throughput requirements or other features. The criteria we're going to cover are low power modes and computing efficiency. Shown here is a graph plotting low power versus speed. Yes, that is low power on the y-axis, which is the desirable output. That is, decreasing power is depicted upward in the y-axis. Represented with the green line is the power consumption versus speed trade-off that exists for any given technology. Efficiency is the product of the two and has a vector shown here in red. Efficiency increases with advanced technologies and architectures. This is what shifts the green line in the efficiency direction of the red arrow. There are efficiency increases the system architect can make as well. That is to apply techniques in software and hardware, such as the switching regulator that we just discussed. Although, in that particular case, it affects the overall system level efficiency and not just the processors. At the hardware architectural level, one has to familiarize themselves with the microcontroller's various modes of operation. Some manufacturers have different names for the various modes, but these are the more common names and their characteristics. The higher up this list, the more power is consumed, but these modes also have more features and higher throughput. The graph on the left shows the processor's activity over time. Any given application may have a dominant mode of operation that dictates parameters you should be focusing on. As you can see, if your application is very active, that is, has a very high active duty, then the power consumption during sleep or standby is a minor consideration, as evident by the table in the upper right. Yet, if you have an application that is awake for only 1 second per hour, then you should be focusing on a microcontroller's sleep current capabilities and modes. If your application requires a very active microcontroller, then efficiency processing is very important. You will likely want to compare different processors. That's where benchmarking comes into play. There are 2 basic types of benchmarking to consider. Let me first say that benchmarking is not an exact science. One size does not fit all. Ideally, you'll want to perform your application code on every candidate processor, but that's not always practical. Also, getting usable benchmark information from manufacturers can be difficult at times, and not all manufacturers use the same benchmarks and measurement methods. However, you can get enough information to make some informed decisions. Many of the processing-based benchmarks have been around for some time now. The first 2 on this list have their issues and are not highly regarded. The CoreMark benchmark, on the other hand, is highly regarded as a very good indicator of processor throughput. A consortium maintains the trademark and copyrights. Therefore, if you publish your results, you have to have had used their code exactly as it is provided. Power efficiency benchmarking adds another dimension. Many manufacturers publish a microamps per megahertz benchmark. However, megahertz is not a useful metric when comparing 2 different architectures. Also, manufacturers don't always run the same code for both the throughput benchmark score and the current consumption measurement. They sometimes execute different code for each activity. Many execute a while one statement during the current measurement, which hardly exercises all the internal circuits. Some will run a prime number algorithm, a Fibonacci sequence, or simply state that it was measured while data processing. A true benchmarks per milliamp is a nice controlled benchmark, and many manufacturers are starting to publish their current consumption specifications while running the same benchmark code. It is perhaps the best way to determine a processor's real computing power efficiency. The CodeMark benchmark code is licensed by the nonprofit Embedded Microprocessor Benchmark Consortium, or simply the EMBC, which they pronounce as Embassy. The EMBC website is a good place to get more information about the CoreMark benchmark. But perhaps the best thing about this website is that they have a long list of published CoreMark scores. At last count, they had over 450 scores published on their website. This is a bar chart I put together from CoreMark scores I obtained from the Embassy CoreMark website and from datasheets. The microcontroller with the green bars next to them are the microcontrollers with a true CoreMark per milliamps score, because they have had published both a CoreMark score and a current consumption specification that was measured while running the actual CoreMark code. The Atmel SAM D20 is a bit of a Rosetta Stone here, in that it has a couple of published current consumption values. One is while executing the CoreMark code, and the other is while executing a while one statement, shown in blue. An indicator, if nothing else, of the disparity of the two measurement methods, and perhaps a scale in which to translate other benchmark values, although I recommend you apply it with caution. I should mention that the CoreMark benchmark is integer-based, so if you need a floating point unit, then you will probably want to choose a microprocessor with a floating point unit. The top 3 microcontrollers in this chart do have FPUs, but obviously the CoreMark scores, that is, the data processing efficiencies, have nothing to do with that fact. On the bottom of this bar chart is the Intel 8286, which I've included just to show how processors have advanced in the last 32 years. The next two up on this list are 8-bit microcontrollers, which don't really compete in this space. Their value is more in the price and/or sleep current regime. At the top of this chart is a very special case. This is a good example of what an ASIC can do when designed specifically for a focused task. This is the benchmark score for the Synopsys EM4 processor core embedded in an ASIC for P&I Sensor Corporation's Central Motion Coprocessor Sensor Hub. Unlike a general-purpose microcontroller, this was designed and highly optimized for its task. For instance, it has only a couple peripheral functions and operates at a fixed speed with 2 highly efficient internal clocks. The single speed and short route lengths allow the clock tree and data buses to be highly optimized, which greatly reduce dynamic currents. Listed here are important points to consider when choosing and using benchmarks. I mentioned earlier that there are techniques you can apply as a system architect to get the best utilization from any given microcontroller. In many cases, voltage scaling could yield the highest impact on your design if the conditions are right. Because of its potential, I'm going to cover voltage scaling next, after which I will briefly discuss software techniques, and finally I will touch on other power-related considerations worth reviewing. Switching transistors, such as those found by the hundreds of thousands, if not millions, in microcontrollers, have both static and dynamic currents. Static current includes all transistor leakages and bias currents, as shown by the arrows in the schematic on the left. Dynamic current is current that arises from the charge and discharging of CMOS gate capacitances, as shown on the right by the red arrows and the electrical model of the typical CMOS gate. The power loss is due to unrecaptured charges transferred at each clock transition. The gate capacitance is charged in the first clock transition via path I1, then discharged or dumped in the second clock transition via current path I2. Dynamic current is dependent and proportional to several factors as shown in the equation below the diagram. One is capacitance, which is a semiconductor process size dependency. 2 is voltage, which is highly enforced by Ohm's law. And 3 is clock frequency, because more transitions means more charge being utilized and dissipated as heat. However, consider this. The faster the clock, The higher the processor's throughput, the quicker a particular workload will complete its task, and the less often the processor has to operate, which makes this a wash. Bring us back to the first two, which is capacitance, which is processor size dependent, and voltage, which is something we may be able to control through voltage scaling. So let's look at this another way. Here I stack the response of a dynamic current versus frequency plot on top of a constant static current to get a picture of the total current versus frequency. Remember that dynamic current is proportional to clock speed, which in turn is also proportional to the amount of work being performed, also known as throughput. That is, as frequency increases, the number of instructions per second executed also goes up. However, IQ, or static current, remains the same. Because of this relationship, one important fact comes to light. That is, the ratio of work output to worthless static power dissipation increases with frequency. It is reasonable to say then that higher frequencies yield higher efficiencies. Generally speaking, that's true. There are some things that do impose limits, but that's another topic. One important consideration regarding switching circuits is that higher clock frequencies require higher operating voltages. This in turn also causes disproportionately higher power consumption. The reason one cannot use lower voltages at higher frequencies is that higher drive voltages are required at higher frequencies to maintain timing integrity. We know if we reduce the voltage of our microcontroller, specifically its core voltage, we will lower its power consumption. However, we also lower our maximum allowable clock rate. Many microcontrollers that support voltage scaling are done so at discrete voltage levels. Hence, there are discrete steps in the frequency versus voltage relationship. This diagram is an example with one discrete step. We know from an efficiency perspective, referring to the static versus dynamic current ratios, that point A is the most efficient. Point B is not as efficient as point A. However, for times when you need high throughput, point B is the best operating point. Here is an actual voltage scaling versus frequency example. These are values for an STM32L152, a Cortex-M3 by ST Microdevices that supports 3 internally controlled core voltages. Note the absolute current efficiency on the left axis and the relative efficiency figure on the right axis, which is normalized to point A. There are several things worth noting on this graph. In the 1.2 volt curve, the green curve, the efficiency drops off rapidly as it approaches zero frequency as static current becomes relatively large. Also note the relative power efficiency from point A to point B to point C is negative. So the message here is run as fast as you can for any given core voltage. Also, choose the lowest core voltage that can support the workload throughput requirements. This graph shows the active duty cycles of the same 3 core voltages operating at their maximum frequencies with a hypothetical fixed workload with the requirement that the code is processed within a given amount of time, shown here as one process period. Lower operating frequencies yield better power savings, but can it support the throughput requirements and is the latency acceptable? This slide shows an example of both. For a given hypothetical workload, the highest core voltage running at 32 MHz will get the workload done fastest. Obviously, the 4 MHz rate takes 8 times longer for the same workload, and in this case cannot complete the workload in the desired process period. The 16 MHz rate is a better choice as it can get the prescribed work done within the allotted amount of time. However, it operates more efficiently than the 32 MHz example. Although it does have more latency than the 32 MHz rate, for many applications this is not an issue, even less so if the latency is consistent. This is a list of just a few software techniques you can apply to lower your power consumption. There are many great application notes and articles on the subject of low power design written by engineers, primarily from semiconductor companies. Many of them focus on their particular value proposition. I have a few favorite sources which you can find on my website. This is a list of other considerations. Again, I'm presenting the 3 most widely important topics to understand from a general sense. Some of these issues, options, or constraints listed here could easily be just as critical or useful for any given situation. And that's going to wrap it up for part 2. Thank you for listening.